Hey, Dr. B here, and let's talk about limiting and excess reactants and how to calculate it for a given question using a FAST method. Now, this method may not be for you. It requires a certain amount of memorization and a comfort with the numbers. If you don't like it, just use the normal method that I showed in the previous slide. If you do like it, it's a big time saver. Let's have a look. We're burning some butane, so we're going to take 100 grams of it. We're going to combine it with 100 grams of oxygen. And the question is, how many grams of carbon dioxide will it make? And they let you know it's a limiting reagent problem because they're asking also how many grams of whatever will be unreacted. So the traditional way is to find out how much carbon dioxide you can make from this, how much carbon dioxide you can make from that. The lower number wins, and then you do a separate calculation. It's time consuming. Here's a faster way to do it. Write a balanced chemical equation. Butane reacts with oxygen to make carbon dioxide and water. Balance it. It takes a little bit of time. Now simply write the molar scale amounts so you can get a gram ratio of everything. That means do 2 times 58 here, since C4H10 is 58 grams is a mole, 48 for the carbon, 10 for the hydrogen. So 116 grams of this will require 13 times 32, or 416 grams of that. You need almost 4 times as many grams of oxygen as we do of butane. And by the way, we don't have that. And how much carbon dioxide will it make? I guess we care because it's asking for it. So that would be 8 times 44. The 44 coming from 12 plus 32. Good. And I'm just going to skip the water because it doesn't show up in the problem. Okay, fine. Now, by inspection, figure out the limiting reactant. 100 grams of butane would require something like 400 grams of oxygen, which we have much less of. So it's the limiting reactant. It's going to completely get consumed. We now have a scaling factor. Instead of doing it on a 416 gram scale reaction, we're doing it on 100 grams of reaction. That's what actually gets consumed. So it's about a little less than 25%. Instead of making 116 grams of this, we'll make a little less than 25% of that. There's our scaling factor. Apply that to your 116 grams. We'll use 28 grams, but we started with 100, so we're figuring out that 72 grams remains. It does ask that. Our scaling factor, instead of making 352 grams, we're going to make a little less than a quarter of that, which is 85 grams, and we are done. The combustion of 100 grams of butane with 100 grams of oxygen will produce 85 grams. There it is, 85 grams of carbon dioxide, leaving 72 grams. That should be 72, not 27. Little switch there. So make that a 72 grams of butane. That's our excess reactant, unreacted. Let's apply it to a second problem. Make sure you put 72 there rather than 27. The combustion of 50 grams of butane with 500 grams of oxygen, same balanced chemical equation, so I already wrote it down, will leave how many grams of whatever unreacted. But this time they're saying 50 grams of butane, 500 grams of oxygen. That's 10 times as much oxygen. We only need less than 4 times as much oxygen. We got plenty of oxygen. The limiting reactant is the butane. It's all going to be consumed, and that's our scaling factor right there. Instead of doing it on a 116 gram scale of that, we're doing it on a 50, so a little less than half. We should consume a little less than half of the oxygen, so 50 divided by 116 times the 416 will use up 179 grams of the oxygen, leaving 321 grams of it unreacted. That should show up somewhere. And similarly, we're not going to make 352 grams. We'll make a little less than half of it, or 152 grams of it. We got it all. This reaction will produce 152 grams of the carbon dioxide, leaving 321 grams of the oxygen unreacted. I hope you like this method. This is a fast method for doing a complete limiting reactant problem.